Hello and welcome to the course. In this video, we're gonna model the ground roll in MATLAB. Here you can see our pseudocode, let's say, or block diagram. According to this, we will build our MATLAB code. So let's go to the MATLAB. Okay, recall that this is our initialization part, and we will build on this code. So let's get started. I'm gonna create a section break here. I'm gonna call that as ground roll. And let us print to the console that we are at the ground roll. So let's say phase 0.2, which equals to ground roll, semicolon. So let's look at the MATLAB code. I mean, not the MATLAB code, of course. The pseudocode that will create us the MATLAB code. This is better. Okay, I need to calculate the vstall here, and vstall is stored in the symlog. So let's create a new variable and call that as vstall, and let's say reference is equal to. Now I'm going to pull the stored data from symlog, and that will be symlog. It's stored as states, and finally vstall. This is done. Now I need to create my while loop here. To do that, let's say while, and let's end that. Okay. And while v is smaller than 1.1 times vstall, and we need to also extract v from the symlog. And to do that, I will copy this and paste here, and v is stored as v, which is velocity. And now I can write the condition here is smaller than 1.1 times vstall. So I can copy this and paste here times 1.1, and this is my condition. Inside the while loop, I need to perform my Euler integration here. And to do that, let's go up. I have some initializations here. Let me copy those and paste them here. I need the next steps. And for that, I need the previous steps. I have the previous steps already, so I will keep those. So I will copy those actually via this and paste them here. Okay, these will be I plus 1. Where is the plus? Okay. And copy this and paste for every I here. Okay, I have the previous states here. Now I need the derivatives that are also stored in the symlog, and that's calculated by the flight dynamics at the very first start of the simulation. Let's have them actually. They're stored as symlog.derivatives, but this is quite long, so I'm gonna define a new variable, which is derivatives simply. And I'm gonna allocate that to symlog. Let me copy this. Not times dot derivatives. Okay, now I can use this variable, and let's add that here. Okay, derivatives times, no, I didn't still unpack derivatives. For x, the derivatives I stored is x dot e. Okay, this is the derivative for x. And do not forget the dt here. So dt. So I'm going to copy this and paste for every variable here. And I'm going to call their own derivatives here and wait for that, please. Okay, it seems we are done. And finally, do not forget to integrate the time as well, which is defined where here. Let me copy this and paste to here. But this will be I plus 1. I plus 1. And this will be time I plus dt, of course. Okay. So let's go back to our slides. we need to pack our environment right now. To do that, let's go back to our code and let's go up. We have already calculated the environment here. I'm going to copy that and paste here. And I'm going to say that this will be I plus 1, and finally the I plus 1, because we are dealing with the next step right now. This is the calculation, but we need to pack. And to do that, I'm going to only pack the row, which is the density. And let me copy that and paste here. And finally, the speed of sound, which is A. Okay. We have packed the environments. Now it's time for the controls. For the controls, again, we have defined the control setting here. I'm going to copy that and paste here as well. The controls are the same. We don't have any change. The still afterburner on. We're still taken off with the maximum power, and the elevator is not deflected because I'm not generating any lifting force during the ground roll. And the only force that creates the moment is the lifting force in our case, and therefore no lifting force, no moments. So I don't have to deflate the elevator. And finally, I don't have to use any controller for that. Okay, but we have an extra control setting, which is called as control gear, which is the landing gears actually, and they're deployed, and therefore it is 1.0. Okay, the controls are also packed. Now we depack the states, and to do that, again, I'm going up, and I have the states here. I'm going to copy those and paste here, but this will be I plus 1 again. So let me copy this and paste for every state I have here. Like this, and finally for this. And let's don't forget this. Okay. The next step. Now I can call my flight dynamics function, which is my physics engine. And to do that, again, I'm going up. I'm going to copy this and paste here. Okay. And finally, I need to increase the iteration and save the output to the symlog. So let me copy this and paste here, and above a bit, let's say I is equal to I plus 1. Okay. Let's go back to the slides, and yeah, we're done with the ground roll. So if I run this code, I should have the plots. And for that, I need a post-processing part, but I already have that here. But before of it, let's run the code. Then I will show you those codes. I mean, we don't have to lose our time about speaking those post-processing and visualization part, which is the plotting. So let me run the code. Okay, here are the results. So let's examine one by one. Okay. The angle of attack is 0, the pitch angle is 0, and the flight path angle is 0 because we are still on the ground and we're simply accelerating. There is no elevator deflection. We have no lifting force, and we have a slight drag force. Our normal force is negative, which is correct. And this is probably my weight, and this is my thrust, but I've lost the labels here, legends here. Where did it go? Anyways. No elevator deflection, no aerodynamic moment. And the specific consumption is increasing because the thrust is increasing. Okay, the fluid flow is increasing as well, because the afterburner on. And throttle setting is set to 1, and it will be 1 until the end of the takeoff because we are taking off with the afterburner on. We have a huge acceleration at the very start, and it slowly decreases. There is no acceleration at Z because we're not taking off. The ground speed increases from, in case 5, because we've defined 5 here, right? Yeah, I can do that 0.5, but it doesn't simply change anything. I mean, the behavior is still the same, but we can change that later. Okay, there is no climb rate because there is no vertical velocity. Trail speed, therefore, is equal to ground speed, and it's the same. And we have Mach number. We have reached about 0.25. I mean, we are accelerating very fast. And finally, mission trajectory, we are still on the ground. No penetrating to the ground, no increasing altitude. We're going simply forward. Okay. We are done with that, but let's look at the post-processing part. So what we do to plot those plots, let's say. To be able to plot, recall that from the flight dynamics function, and let me show you that by calling the flight dynamics function to you. That's here. At the very end, we packed a lot of variables here. And the reason was the plotting. And let's go back to the workplace, and everything is stored in the Simlog. I need to unpack the state variables in order to plot them or have them in the workspace. And to do that, simply what I packed here, I unpacked. This is only that. There is no extra thing. There is no complicated thing here. The post-processing is this. And like I said, the states are unpacked, the forces and moments are unpacked, and finally the derivatives are unpacked. I mean, we unpacked derivatives here already, but this is for, plotting. For the visualization part, we need to call our plotting functions. In here, I converted the seconds to hours because, okay, at the very start, in the takeoff, the seconds are important, but when I consider the whole mission profile, I need to have the time as hours. But for our case, I can delete that. And let me delete that, actually. Instead of deleting, actually, I can comment that out. And let's change the velocity here to 0.5. And this will be okay. I can rerun the code. And also, let me close this because we will rerun. Okay, I'm going to create my figure here, and I'm assigning a name to it, which is the mission profile analysis. And this is for fanciness. And for plotting, I'm going to call the tile layout. This is a great function. This has nice features, actually. And let me show you that feature to you. If I run the code, what happened? All right. Because time h is defined in the plotting functions here. So instead of doing that, let me say time h is equal to time. Yeah, my bad. And I need to also change this as well. Okay, now we don't have any problem. And okay, the feature is, let's go back here. For example, this is how we see the plots. And if I do this, as you can see, the plots are shrinked to A1 window, let's say. And if I play with the size of the window, as you can see, the plots are changing. Their dimensions are changing, which is actually a nice feature to me. And you can obtain that via the function or plotting function type layout. You call this, and to do that, you need this specification, let's say. It's called flow. And for these, again, for a fanciness node, we have title. And the next step is simply plotting everything. We continue with the next tile, and I'm calling my plotting function, which is plot, and time. And what I'm going to plot is the alpha, and recall that alpha is always ready, so I need to convert that to degrees. And the other things are just labels and in the grids. And I plot everything here. What you see in the plots, I plot everything. Anyways, these two sections will always stay in our code. For example, for the next lecture, if we continue with the next section, and let's say it's rotation, this will stay as well because we're going to build on the ground roll. I mean, what we're going to examine, we're going to build the before of it. For example, if we want to examine the airborne, we'd have to build it on the rotation part. And we will do that one by one until the very end of the mission profile, which is the landing. That's all for today. Again, let me show you the plots to you. We have the latency here, by the way. As you can see, this is the weight and this is the thrust. We have a nice amount of thrust to weight ratio here. Actually, it's very nice. It's about, I think, 0.8. I mean, it is nice. Anyways, this is it for this lecture. I thank you too much for your attending and watching. In the next video, we will continue with the rotation part. So stay tuned for that, and I'll catch you later.